So, guys, that's good. Running and beeping. Something else beeping. All right. So anyway, the worm like myself. So let me just do this thing. Oh, there's a pen in here, a Weston pen. Nice. All right. So it's okay, I guess. So we got so basically surfactants. So you start out with the triglyceride. And then typically like lard is kind of the popular one, and there's like 12 carbons off like this. This is C12 carbons, and that's unsaturated. If it's that's saturated, sorry, and unsaturated means you have some double bonds on it. It's like the problem with lard is it's unsaturated, not usually cholesterol, so you know it kills it. That clogs your arteries, right? And if it's unsaturated, that's better, which is like plant oils and things. Anyway, so these things, that's a fatty acid, 1, 2, 3. I guess there's a OHs on these, like 3 OHs. Somehow it's missing a bond, but anyway, that's a fatty acid, which is lard. Which Cincinnati is the largest consumer in the world of lard. Like train loads come from Texas is the largest producer, and Cincinnati is the largest consumer. So like trains going from Texas, from like Fort Worth to Cincinnati. And then the lard, you saponify this and you get glycerol, which is like cosmetics. It's like fake tears, right? And then you get the fatty acids from those things. Right. So basically that can make soap. Oops, OAP. And then if you take that stuff, and then so this and typically that's going to be like a crystalline solid, like it's bar of soap, right? So it isn't exactly good to make like liquid detergents or for like shampoo or body wash, right? So you have to sulfonate that. So you put in SO4, and you have and the end ends up with sulfur, and then the 12 carbons, which is called dodecyl or laurel. LAURYL. Thanks. I always spell that wrong. So anyway, dodecyl means 12. Laurel is some Latin word for 12, I guess. You know, and then because it's sulfate, and then you swap off the hydrogen. This would be S double bond OOH. You kill that with a sodium salt, and then you end up with sodium, the SDS. That's like the most popular surfactant. And then so that's an anionic surfactant. So this is minus, and this is anionic, which is better for you than cationic, because cationics typically have a tertiary amine at the end instead of a sulfate. And the tertiary amine is like a carcinogen or something. So CTAB is a cationic alternative to anionic, basically to SDS or SLS. Right? And then in the shampoo business, they usually put an ether here, so they'll pop an ether link right there, and that makes it into SLES, which is like it's a softer shampoo, I guess, or something. Somehow it's better. And then you can also mess with this structure here, do all kinds of things. But this paper's working with SDS. Instead of a sodium salt, they're using an aluminum salt, and he says that that's because sodium only binds with one head group. So this is called, so you have this kind of sulfate head group, and then this alkane tail. So this is hydrophilic, and this is hydrophobic. Right? So this is oil, that's water. Basically, they don't want to be together, so it's kind of an internal animosity within the molecule. So if you put it into water, this stuff wants to go to water, this wants to run away. So the tails want to just cluster together. Right? And then the heads want to be on the outside if they can do it. So this all depends on kind of the geometric packing of the thing. So you have sodium counterions floating around out here. And then these are all negative. So you know that there's a Debye screening length involved here, like lambda, and the higher the concentration of the counterion, the less those charges matter, and then the structure is going to be disrupted. So you can think of it as an ionic. So the ionic charge is kind of like a size for this thing, like kind of Debye length gives it a size, and then it wants to minimize this interface, so it wants to make spheres. So normally you want to get rid of the interface when you have two-phase systems. This is like a micro-phase separated system. You want to minimize the interface. So spheres would be the best scenario for that, right? So, but if you start adding more salt in, so you can either add more salt or add more surfactant. Either way, the structure gets disrupted, the crowding becomes weird here, and then it starts to form elliptical micelles, which are the same thing except shaped like that. So the tails fit in, and then somehow it decides a length for the thing. And if you put in enough salt, or you put in more salt, that gets longer and longer, till finally you get kind of a micron size length chains. So that you end up with this just like that, where that distance is a micron, like pretty big. So 1/50 hair diameter. So something you can almost see. You know? And the thickness, that distance is 1 nanometer, the diameter of it. And you'd think that this thing would just be like pretty flimsy, like it would, because it's just made up of these stupid little charge things. But actually, they're pretty robust. So it's actually, this is almost like a permanent structure. So weird stuff happens. So as you increase the concentration, so it starts spherical, it goes elliptical, and then it starts forming these. And as you put in more and more either surfactant, so concentration SDS or the salt, so you can add more salt, like add salt to it, and then it'll make these things longer and longer, right? So they aren't, it's not fixed in size. So you say, right, so they can entangle, they reach a certain molecular weight, and then you can get entanglements, and then they behave just like a polymer. That's why the shampoo is like an ideal example of a polymer. Like if you take one of the features of a polymer or viscoelastic fluid is that the bubbles in it aren't spherical, so you have like normal stresses that develop. So if you take the shampoo, turn it upside down, if it has little bubbles in it, this used to be in the Prel ad. So they showed this like it would be like a balloon, right? So that's because normal stresses are squeezing on it. Like you spin the viscometer, and it's pushing it apart because you're stretching the chains and they want to spring back, so it makes a normal force. That normal force squishes the bubble and makes it into a teardrop shape from one direction, and if you look at it from the other direction, it makes like a chevron thing. So it's this first and second normal stress differences that show up. So again, like these stress differences, like a viscosity, they're just constitutive parameters, and there's no understanding for them. It's just an observation that the things do this. Why they do that is kind of weird. You know, like why there's no difference between, it doesn't have a coordinate system to it, you know, so basically that happens. And the same thing when you extrude a fiber, it has die swell, so it's the same kind of normal stress. And also there, the fiber isn't going to be circular when it comes out, and cross section is going to be elliptical because of the same reason. The normal stress is unequal. For some reason, it decides a coordinate system, and it makes it elliptical. Right. So this shampoo is like a perfect example of a viscoelastic fluid, and it has no polymer in it at all. You know, if it did have polymer, then it would be like hand sanitizer leaves like a scummy thing on your hand afterwards, which is the polyethylene oxide PPO polymer. Right. So that wouldn't be good in a shampoo or body wash stuff. So anyway, so that's why. So basically, like P&G and oh, I never remember the name of the British company. It's a P&G British company that does soap and stuff. Lip
C?
starts with C.
Does it?
No. Did I write C?
No.
No, it's like begins with, it's like L something. They're a big company. I'll remember in a minute. Anyway, those two companies fund. So there's a lot of work in UK from them and from P&G in the US. And then P&G also has like research lab in Belgium and then like something in England. So they're funding both England and US and Europe. And then these guys have a factory in New York. So they're kind of doing some money in US. So there's kind of cash in this involved. And anyone that does rheology, this is like a prime example of material. So you just do this, you know. Anyway, so that's kind of like part of this. But there's a problem, right? So what he does in this paper, the first thing he does is he does a Zim plot of these things. So he goes to say like, this is a Zim equation. Okay, so this is kind of like, so exponential of something squared times q squared. Let's see if I can. So exponential of something squared times q squared equals, if you expand it, if this thing's small, it expands as 1 plus that thing squared times q squared plus, so that's the first one times the thing squared by 2 and cubed by 3 factorial. So that's basically Gounier's law in a sense, right? So this is Zim function. So we have 1 over, so R is the intensity. So 1 over the intensity is 1 over Gounier's law. So instead of minus q squared RG squared, it's plus R squared, and then it expands to that thing. That's just an exponential decay. I mean, it's an expansion of an exponential decay for the first two terms. So you can linearize it into a Zim plot, which is going to be plotted against q squared. And then this is concentration dependent. So the Zim plot has both the concentration and so the last thing is the Zim plot. So it's got concentration and q squared. So you fit this with a function with concentration and q squared in it, and you get the line, and the intercept is the I0, which is the you can get chi from that, and the slope of this is going to be the radius of gyration, because the slope of intensity versus q squared to give you the radius of gyration, and log intensity versus q squared. So anyway, so that's the Zim plot. So you get RG from the slope, and then if you do the different concentrations, you can get the interaction parameter from it. So this is basically like intensity by concentration. So if you look at like the way we did it, it's a little bit different. If you have a single molecular weight, and then you take intensity by concentration and just do a log plot, then you get, like, if it's a polymer, you get -2, then that should be like that. And this intercept here should be proportional to concentration. So no matter whatever concentration you do, it should be the same curve, because you reduced it by concentration. So you double the concentration, you double the curve, until the chains start to overlap with each other. And then at that point, the size you see is this kind of concentration blob size, because above that size, you can't see the chain anymore because they're overlapped. Right? So then that means you have to get a smaller size, means you have to go over here, then you get this curve. And so this thing should drop with concentration. And if you fit that with Gounier's law, so you're going to get like that's Gounier's law, you get a smaller RG every time. So you'd expect to see, so he's calling like RG squared by 3, this correlation line, because this isn't an RG anymore. It's this weird thing with the overlap. So he plots the correlation length versus concentration, and you'd expect it to be flat. That means there's no overlap. Then you reach overlap, and then there drops. Then that number is C star, where the things start to overlap. That's what he's trying to do. First thing, he tries to determine the overlap concentration from this thing. So he's got those curves, and then he plots the size that he gets from that, which is the slope in that plot. And he gets this curve. Okay, so he gets a drop. That's good. And he says the peak is where his overlap concentration is. What he doesn't mention is that, so as he increases the concentration, his chains grow. So it's not one molecular weight of chain, right? And also the polydispersity is pretty high for these things, because there's everything from a very small chain to very, very long chains, right? So whether or not you can use this approach to talk about this kind of thing is is pretty much a gross simplification, right? So in other words, you're going to talk about the viscosity of this. The small ones matter, like they're going to dilute it and things. So anyway, so it goes up because the chains are growing, and then it goes down nominally because it's reached overlap, and then you're just seeing the size get smaller as the overlap eats into the structure, so you can't see as much anymore. So that'd be nice if that was true. In actuality, something else happens. So when you, and he mentions this in the paper, so something else happens with these particular systems, and when you, so yeah, you start small and then they get longer, and then you reach a point where they start to branch. So these things will branch. So basically the branches are really weird branches because they're completely mobile, because this thing isn't a covalently bonded molecule, it's ionically stuck together little surfactant things, right? So basically this thing has complete, total, utter freedom to move around apparently, which means that this chain that was huge all of a sudden becomes just those pieces as kind of the things that contribute to viscosity. So once you reach a certain concentration of surfactant, the branches happen, or of salt, and then all of a sudden the viscosity drops. And he shows that kind of in his paper here, and he mentions it too. But basically, if that's happening, then this Simplot thing is kind of screwed up. Like it isn't so simple, right? So he's kind of selling it that that's a really simple thing. He shows this viscosity thing. Let's see. Right here. Here, no. It's a plot just like that. It's got 3 parts. Here. So this is way so normally this thing shows a sharp peak and drops. And for his case, it kind of goes up and drops. And he mentions that the dropping, so this is the zero shear rate viscosity. So if you, for a viscoelastic, you're expecting this, if you plot the viscosity versus shear rate, and we have log, that's a log plot. So we have the plateau, this kind of zero shear rate viscosity, and then you see follow up through the, like, Ganny dot to the -2 point something. Right, and there's a transition point, and that's our magic gamma dot star, which is our frequency star, if you're doing that. And that 1 over that frequency star is the kind of a viscoelastic relaxation time of the system. And so that's kind of where the entanglements can relax once you get to times longer than that, or frequencies lower than that. So basically that's the point where the thing acts like a fluid. And then this is kind of where it starts to look like a solid, or it starts to, the entanglement starts to impact it. Right, so anyway, that's the thing he's plotting there, is that plateau number. I should have a sharp peak and drop down. His kind of goes up and down, which is okay. So anyway, so that's good. So he's got parts good, parts like kind of iffy, I guess. And also the other thing is that this stuff it's been studied, like significantly previously studied. So it's hard to tell how new what he's talking about is, but basically in the end, he gets into some stuff that's kind of new, right? So what he's doing is he's going to use like 3 techniques here. So he's got the normal oscillating rheometer, low amplitude, small amplitude oscillatory rheometry, and then he's got 3 things he does. So I guess that's kind of part of the nuance of this. So the one thing is he just does dynamic light scattering. So he measures the relaxation times on this. So this is, I think this is a DLS one. Normalized intensity of SDS in a crystal solution, different concentration, scattering angle. So he's just getting the relaxation time here. So in the DLS, he gets G2. He's going to convert it to G1, and then he's going to fit G1 with exponential decay, which is in the supplemental. That thing, it shows up when you don't want it. It's like opposite intuitive. This is his fit. So he's going to fit with these exponentials G1. G1 is G2 minus 1 minus, see, G2 is 1 minus beta times G1. Beta is an instrumental number. See, G1 and G2 are related by algebra. And then G1 you fit with this each exponential decay. He's got 3 exponential decays. So it's kind of 3 decays, and this is like 1 there, 1 there, 1 there. So what you do, so he's going to get a tau from that. and then the tau, if it's diffusion, the tau should go with q squared. So you plot the tau that you get from that exponential fit, which is just a knee here, versus q squared. And if that's linear, then that's diffusion. So he's got q log of that versus log of that. The slope is 2, means like this goes with q squared. That slope's -2. So you have 2 here, 1 there. So the slope 2 would be like that. So that's what he calls tau fast, because it's at short times. And then he has tau slow, which doesn't change with q, right? So tau slow is like a bulk. He explains it. So this, I've done this measurement before, and I always thought that this, because this is a slower thing, I thought that was like a lateral diffusion of the chains, but apparently it isn't. Apparently it's like a bulk. He shows that it isn't in this paper. He shows that this number, tau s, corresponds with the number I showed you for the viscoelastic relaxation time. So it's not dependent on concentration, so, or on Q, because it's a macroscopic. It's interesting that he says that. So it kind of makes sense. So this thing doesn't change with Q. That thing's diffusion. Right? So you can get the diffusion rate of these worm-like micelles from this thing. Anyway, so that's not the only thing he does with these G things, right? So what he's going to do DWS with it. So he's got and DWS, what he wants to get is this mean square displacement of the worm-like micelle. So to do DWS, all right, so first he just he does something I haven't seen done before. He does DLS microreology. So he takes 0.001% of monodispersed polystyrene spheres, throws them into the thing. And the spheres have much more contrast than the polymer, than the worm-like micelles that are in there. So he just sees one of those spheres kind of moving around all independently, right? So, and then he does DLS on that and gets a decay function for that. So you can get G1 from that. So he does 3. So he does normal DLS. He does this DLS microreology. He does standard oscillatory rheometry, and he does DWS, which is like when you put in a shitload of spheres into it, so many that it's just like white. And then you shoot the beam through it. When you shoot the beam through it, there's no beam that comes out the other side. All you get is like a glow. And from that, there's a very complicated analysis that can also get you R squared, okay, by a guy named Weiss, who did it. And his papers are in there if you want to look at them. But basically, if you put in one bead, it's a much simpler thing. G1 converts directly to this R squared of T. So that's a real function. So you want to get from this G prime, G double prime, which is a complex, that's a complex modulus. Like complex modulus is G prime plus I times G double prime. Like the loss modulus is like if you take the loss modulus divided by the frequency, you get the viscosity. Right? So it's a complex number, but he's measuring a real number. And so to change a real number to a complex number, they do a Laplace transform. So you want to get the complex version of this mean square displacement. So that mean square displacement, so there's a lot to this stuff. Let's see, I wish that wasn't there, or if this was like a little bit lower there. This is some people that aren't Weiss, that are from Johns Hopkins, and they're biological people. I mean, a nice thing about these microreology is you can take a cell and you can do microreology like inside the cell, looking at like some component in the cell moving, right? And then you can say the viscosity within a cell. You can do a dynamic viscosity within a cell, living cell, you know? So it's like you can do kind of crazy things with it. Also, it gives you this really high frequency. So you'll see it adds on to the frequency spectrum of the mechanical one. But this shows, the reason I'm showing this is that, so this guy uses DWS, but he also uses a thing called laser deflection particle tracking to get this R squared in time with real parameter, right? So what he does is, it isn't in the paper we're looking at, but it's interesting to look at. And this is also one of the first of this kind of microreology techniques using particle tracking. And there's a lot of different versions of it. In fact, if you Google, which I did, this thing that he calls LDPT, Like there's no wiki page for that. Like that isn't something anybody does, right? So, but there's a ton of microreology. Like people take a picture, say you have a bunch of beads flying around, you take a picture of it, and you take another picture and subtract the two, and then you can get the displacement of the beads from that. So you can have a video, kind of a very fast frame video. You can get this R squared of like thousands of beads all in one shot. And then that can give you this thing too. So that's so many different ways to do it. But this guy takes a laser, shoots it through the microscope, like where your eye would look down, not so that it blasts into your eye. And then it focuses the beam onto a particle. And he has an XY stage. It can move in microns. So you can get a particle, a perfect bead particle to be centered exactly on that laser. And then when the particle kind of shakes, like it's just vibrating here, he can map the deflection of it by the light that comes off. And he uses like a correlation function to do that. Basically, it's just a way to do particle tracking. He shows that his particle tracking doing that matches with the DWS method, which I'll talk about later. But anyway, this is the DWS was invented by this guy Weiss. So I guess he was at Exxon Research in Annandale. And then he went on to go to, I thought he was at Penn, I think he was at Penn. So he must have gone from Annandale to Penn or something. So let's see, this thing is like the Bible kind of referenced in our paper. It's like Weiss describing DWS. The only part of this is it's like 71 or something. It's from a book. It happened to be on the internet somewhere. So, but otherwise it's inaccessible, like it's not in OhioLink. So this equation, so the simplified version of that equation is that equation, which takes, let me see if I can blow it up more. This is in our paper. It takes, so the measurable parameter, L you can calculate, L star, I don't remember what all the things are, but our paper uses this equation. He cites this paper to talk about it. So you can, if you want to read about it, you can, but basically that's where the thing came from. Anyway, so the first thing it does is just stick those beads in, do normal dynamic light scattering, use this function to get R squared. And then you want to get the complex values from that. So you Laplace transform that, right? So Laplace transform is this thing. So basically it looks like a bunch of exponential decays. And you say, I have my thing in real space, I'm going to convert it to the frequency of the decay, like the tau of the decay. So it would be T over tau. So you get a bunch of relaxation times for the thing that you're looking at, like the whole spectrum of them, right? If S was a real number, that would be a simple thing, right? So, but S in the Laplace, S isn't a real number. That's how you get a complex frequency thing over here that's got loss and storage in it. So S is a complex number. And if you read this, it doesn't say it until the end. So let's see if I can find it. Oops, did that do it? No, it did something very weird. Anyway, I can find the end. Yes. Go down here. I think you have to kind of know this to figure out like how they do this, because it doesn't seem believable that you could possibly take a real decay and then get the complex decay from it. So his S is actually sigma is a real part, and then IT or something is sigma is a real part. I tau is the complex part, I guess. So they're both exponential decays, but this one, if it has an I in it, so if you have e to the minus I something times something, so it's unitless, that's the same as sine of the thing plus I cosine of the thing. So this is a sine function. In fact, if you didn't have that one, that would be a Fourier transform, which is just a sum of sine functions. So it's what it's saying is that you have a displacement. So you have these decays. So there's something's moving. If there's just one, then it just like moves and slows down. So it's just a decay function, and it's moving, translationally moving. When the I is a sine function, it means it's vibrating. So you have a vibration and a motion at the same time, and this thing's allowing you to pick those two apart from a real function of watching the particle move around. So some part of it moving around is shaking, some part of it moving around is actually going somewhere, although it's going in a Brownian walk going nowhere, right? So, all right, so that's how it's done. So basically, if you can do that transform, then you get this complex function. So you have the R of real space, and you convert it through that Laplace transform into R of complex space. And then once you have R, so that would be R with a squiggly line over it, wherever that is in here. It's definitely in here. That's too late in this paper. All right, so R the squiggly line here. So this R squiggly lines of the Laplace transform of R of t, which is a thing that's relatively simple to find. And this is R. So this is just directly the G of t gives you R squiggly, which is the Laplace transform. So that's a complex number, and that's a real function. So basically, you can get the complex R, and from the complex R, then you use that crazy function to get G prime and G double prime. He tells how to do it in here someplace. So it's kind of like a one step. All right, so it's a complicated series of steps. You get G2, from G2 you get G1 using the Siegert relation, which is that 1 minus G1, 1 minus beta G1 is G2. 1 minus beta G1 squared is G2. G2 is the thing you measure, G1 is the thing you want. And then from the G1, you convert it to a real space displacement of the particle. Then you Laplace transform that thing to get the complex number displacement of the particle, which is vibration and translation. Then once you have that number, you convert it to, how do you do that? You convert it using, use Weiss's stuff to convert that number into the storage and loss modulus. Once you have the complex and real, then it's just a conversion of that displacement into the moduli, which works out somewhere here. So anyway, that's kind of the deal. He shows in the supplemental, I guess is where this is. It's in here somewhere. That's this business. That's his fitting. Maybe it isn't in here. This is just plots. It's pretty well described in here someplace. I don't remember exactly where. Anyway, so we get that. So Then he can get. So he does that with his dilute thing. And he does the same thing with the concentrated thing, but the analysis is more complicated. So Weiss has worked out like how to do the analysis to get G prime, G double prime from the multiple scattering with all the particles. I guess that isn't in here. So anyway, he's going to get these three different. So he's going to get three different kind of curves to compare. He's got the with a lot of particles, the diffusive wave spectroscopy, microreology, G stars. This is the square root of the square of the complex modulus, right? So it's a real number that once you do that. So it's the absolute value of the complex is a real number. You can plot it versus frequency. And then the normal rheology gives you this curve. And then he shows in here like the normal rheology curve, which is like there's a first crossover and a second crossover. So the first crossover, that's the viscoelastic relaxation time. And this thing crossover is normally the tube. So you say like it becomes a liquid again because you're within the tube. So below this part is where the network holds the chains together. So it's an elastic. And then if you get to small enough sizes or high enough frequency, then you see the tube and it's like flowing within the tube. So you can't see the entanglements anymore. It's too small. So it's a liquid. So it becomes a liquid again. So this is like the Rouse time for the tube. That's the reptation time. So you have this viscoelastic and then the reptation. And here it's a solid. Like black is solid, red is liquid. So it's liquid at low frequency or long times. becomes solid when the entanglements can't relax. And if you look at small enough sizes, you see the flow. That's like the standard analysis of that. Right, so if you take the complex of that, it kind of looks like a combination of these two. So it just like goes up, has the plateau, and then this is the mechanical, and this is DWS, and they match pretty perfectly. When he does a single particle, and he has to multiply, so he has to multiply the DLS when he has dilute by 3 to get it to match the DWS. So it's kind of weird. Like he's got, so he doesn't know what the 3 comes from. He plots the ratio of the two there. Yeah. So he's measuring it by 3. He's measuring the same thing by 3 techniques. He's trying to show that they're the same. Right. But what he finds out is one, when he does it dilute, is 3 times lower. And he doesn't know why. He doesn't say why. He just says it's 3 times lower. But it matches once you shift it by 3. So he's got 3 techniques. He's got normal rheology. He's got this thing where he puts a single particle in and does DLS on it. And he's got where he dumps a ton of particles in and does DLS on it. And he can get the complex modulus from all 3. And they agree. The difference is that this thing can extend this by 5 orders of magnitude and frequency. So you can see that crossover point. But you can't see with a normal rheometer because it would rip the material apart if you went to 1,000,000 hertz or whatever, And right, it would just tear, it would burn. So basically the motion due to KT of the thing diffusing around is at a really high frequency, much higher than anything you're used to. So you think of it like, you think about KT, there's bouncing around, but it actually is going like a bee or something, so fast. So anyway, so that's the idea. He does the 3 things, they match up. That's pretty good. That's nice. And then yeah.
These from the top one. So the first one is crossover space, and second intersection.
There's 2 crossovers. The first crossover is the viscoelastic relaxation time. It's where the entanglements can not relax anymore if you go to a higher frequency. So that means where they stick and it becomes a rubber or a gel. Below that, it's a liquid because they can relax. Then you go along, you go 3, like 3, how many? 1, 2, 3. Well, these are doubles. So it's like 4 orders of magnitude and frequency higher. So something you can't hear, and then, or reproduce with your voice. And then at that point, you start to see it becomes a liquid again. And the idea, the theory, so all right, there's 5 theories for why that happens, but one of them is that you've reached the point where you're within the tube, and the chains within the tube are diffusing like normal motion, like they're flowing with Rouse motion. They're just flowing like a train driving through a tunnel. The tunnel's all convoluted, but it's a train through a tunnel, so they flow. So once you get to such a small size, they flow. That's the idea. That's one of 5 reasons why that happens. All the 5 reasons are completely different reasons. And in this paper, so he doesn't mention that reason in this paper, What he mentions, and in biology, they don't mention that reason either. And in this paper, the reason he mentions is something called the bending versus the Zim mode. So Zim mode is something like you just have the chain and it moves through the fluid, and it can have hydrodynamic interactions with the liquid or not. But it's moving through as a whole chain. And then the bending mode is when you've zoomed into such a small size, and you have long persistence lengths of the thing, and then you can see that the persistence length that the thing bends, so it's flexing. It's like a beam flexing. All right, so the problem with that is that the high frequency beam flexing is a solid behavior, not a liquid behavior. And the Zim mode is a liquid behavior. So when you go to higher frequency, it should become solid, not liquid. That's a little bit of a twist of the whole thing that he doesn't mention at the end of the paper. So he spends a lot of analysis talking about that bending mode, the Zim to bending mode transition. Again, there's 5 totally different theories for why this crossover happens. But this one seems a little weird, because they're not actually, I'm not sure that they're really actually talking about that crossover, they're in that same frequency range. The number he gives for the relaxation time of that is the same as this, but the behavior is opposite, you know, it doesn't go liquid at high frequency, it goes solid because you become a beam, it's a flexing beam, it's at high frequency. In this case, yeah, no, not with the beam model, no, it would be a solid because a beam is a solid thing and it vibrates. The Zim model is a liquid flow model, and then at high frequencies for him, you know, so he talks about this extensively at the end. The beginning part of this paper is pretty understandable. And it kind of gets to this Never Never Land part where he talks about the beam, the Zim to beam transition. And then that part doesn't make that much sense because the frequencies are the same as that second crossover, and he doesn't mention the second crossover. Like here. So the Zim model and the bending mode. So he's got these two things, and G star should go with a certain power for the two. So he can plot those two powers and find where it crosses and determine 1 over the frequency would be the time for that. And it turns out that time is similar to the time of that second crossover, which is this Rouse mode for the reptation, right? But so he doesn't mention that stuff. Anyway, so you can get a modulus for that, yeah.
Can you use particle tracking for both solid and liquid particles?
That's a good question. Because the mechanical testing you can do with solid and liquid. I don't know the answer. I haven't seen anybody ever use it for solid. And it's something like, it's almost like when you're doing the XPCS measurement with X-rays and you're looking at the dynamics, right? In a solid. So I don't think anyone's done it yet, you know, but you could do it. I mean, I think you could do it. In that paper, that instrument that he uses for particle tracking is homemade. Like you need a laser, you need a microscope, and then he's got a correlator that costs $1,000. So the whole thing is pretty cheap to make. I mean, people aren't going to beat a path to your door or anything, but basically you could do that yourself. And if you wanted to look in solid state, you could do it. You know,
So
but I don't think anyone's done it.
Other than the motion, what else can we use particle tracking for?
Well,
Can you, I mean, the size, the quantity?
yeah, I mean you're gonna say you get tau, then you can convert tau to a size, a hydrodynamic size, right? So you can get the size, you can get the shape. I mean, if you get the hydrodynamic size, that's commonly used to tell the shape and size. You can get multiple decays in it for different shape things. So yeah, you could use it for a lot of things. But it's a little slightly complicated, but it isn't really that bad, you know? And people that are doing it are doing pretty well, I think, for money, for research and stuff, you know. And then the industrial, like Procter and Gamble had a guy doing this stuff, then he retired. And like no one's done it since then, the DWS stuff. And they just had a commercial machine that they use. So it's kind of hard to tell in a company, like from research perspective, it's interesting, I think. It's what's amazing is that like you can take, like people pound their head to try to get an instrument, you know, that would get to higher frequency and it didn't work. Then you can just do this thing. It's completely, absolutely different. You get exactly the same answer and it goes out so far, you know. So it's almost like amazing that you could do that. But all right, it took like heavy duty math. If you look at the Weiss, if you look through that Weiss book chapter, I mean, it's intense. Like the math is nutty. So anyway, so what else does he get here? So he's comparing the different techniques, and he's also trying to get this model for the structure, right? So the model he has for the structure is like this. So the model's already known. So, but the details of it aren't exactly. So when he's saying like he gets the overlap concentration, that's a little I don't know what color that is, like pinkish orange. Did you see there was like anyway, there's a newspaper article about a new color no one's ever seen before or something, by shooting lasers into people's eyes. But it was a color similar to that color, which I don't have a name for, which maybe the reason. Anyway, so those are the overlap things. And then the mechanical gives you the entanglement, the length between entanglements, right? So you have that length. And then you can get the diameter of the he claims he can get the diameter of the worm like micelle, and then he can get the Kuhn length. And it turns out the overlap size is the same as the Kuhn length. So there are relatively large Kuhn lengths in this. I mean, the diameter is a nanometer, and the length of that I think is it's long. So the Kuhn length is huge here. And the things are like microns in length, the fibers. And then the entanglement length is 10 Kuhn lengths. So he figures that all out from this dynamic measurement. Just kind of interesting. So you can get that whole cartoon of kind of what it is. What he doesn't get is like, and what no one can get is like, what's the length of the chain, right? Because of the overlap, you can't see anything above that. So basically, all you see is a rod. If you did scattering or something, everything else is just smeared out. So he shows a cartoon, but you know, and you can't. If it was polymers, you could deuterate one chain and you could get the size. But because it's not polymers and they fall apart all the time, that's the other thing. All these dynamics, the chains aren't break and form all the time. So the dynamics also include the break forming time constant too, which he doesn't mention that either. So there's a lot of nuances to this, but that's still, it's a pretty comprehensive thing. I don't know. So what else is in here? Let's see. There's a lot in here. What do I have in here? These, I just wrote some questions, but yeah. But
You say something about equation 4 being a typo from the homework in final.
yeah.
How do we rewrite the equation 4?
All right. So equation 4, I was just going to just get to that. Equation 3. I originally said equation 3, but oh, did I say equation 4? That's just the Stokes-Einstein equation. I mean, because diameter is 2 times radius is 6 pi viscosity r. That's just Stokes-Einstein. Except this is the hydrodynamic size. No, that's right. If you swap the size, so that's RH. It's Stokes-Einstein equation. Diffusion constants KT of 6 pi viscosity RH. This is a diameter instead of a radius. But I didn't ask that, did I? Let's see. Let me go through here. In terms of overlap fractant concentration. So I mentioned that the Zen plot's got serious problems because the chains grow and the chains branch, and the chains are always changing too. I didn't mention that, but basically they're always breaking and forming. So the whole thing is a mess. To do a Zen plot on that is kind of insane. It's like you cut a worm in half and you get 2 worms, right? So it's like that. But they're cutting in half all the time, and then also rejoining all the time and branching to make these branches that aren't like anything physically that you normally are experiencing. So the Zen plot's insane to do, actually, when you think about it. But he still gets a number of it. And then the Guinea's law thing I said, right? So and then mean square displacement tracer, he gets that thing, and then he's gonna and he's going to convert that to this complex number, very low tracer, and he uses Laplace transform to get the imaginary frequency one, and then explain what a Laplace is and how it can convert a real, like how do you get real to complex? Like how do you convert that? So it's just that integral, and there's 2 parts to it. And look at it a little bit to convince yourself that it's possible to do that, you know. It's not exactly believable you can get something from nothing. Like you have something, but if you think about it, like the thing's moving around and it's vibrating and it's translating, that's the vibrating is a useless motion. It's wasted, right? So the waste is like the imaginary part. It's like the heat that's given off. So it's the imaginary part. So it kind of can make sense, you know, I guess. Anyway, ChatGPT is a good place to ask that question. And then I've been having conversations with ChatGPT lately. It's like kind of funny. Like it can argue with you, you know, like the green flash at sunset. It firmly believes in it, and I don't. But anyway, he used a Maxwell model to obtain the terminal relaxation time. So just say how that is. So basically, if you take the if you use a Maxwell model and you have that plot, this first, that inset plot, wherever that is. I guess it's here. So this part's fluid. So if you take the complex, the red one, and get the slope there, that's the plateau viscosity, right? And then the crossover gives them the tau, the viscoelastic tau, and then this is the plateau modulus. So basically, from that you can get the molecular weight between entanglements, right? So plateau modulus is that value. The slope of this gives you the viscosity, and the crossover gives you the tau. That's the three things it's asking for. Terminal relaxation time, zero shear rate, viscosity, and plateau modulus. So that's that. And then figure 5 shows the transition between ZIM and the bending. So explain the transition. So basically, ZIM is a fluid flow. Usually, like, the whole chain just moves around in a dilute solution, kind of, right? Which doesn't seem to apply here. And then the bending mode is when you zoom into such a high frequency that you just see rods, which are solid. So you go from flow to solid, which is the opposite of what you see in this viscoelastic curve. So how that fits in, I don't know, but that's a popular thing in biology. So, and he's kind of come from a biology thing, I guess. Then how does that relate to the second crossover? That's kind of an open question. You could ask ChatGPT to explain it, and it doesn't give a good answer. So maybe there isn't an answer to that. It's just kind of crazy. He somewhat convincingly demonstrates that he gets that transition. So then figures compare the screen length and the Kuhn length, finds they are identical. So that means within, so there's this concentration blob, they overlap, and then within one of those blobs is a single Kuhn length, which is odd. That means the Kuhn length is huge. And then that's not a normal situation. From the mesh size, he gets from the plateau modulus, so KT over the molecular weight is the plateau modulus. The molecular weight gives them this mesh size, and that's 10 times the Kuhn length, or 10 times the overlap thing. So that's how he makes his cartoon. Basis of figure 11. Then it just says, like, does that all make sense? Like, can that fall together? Chain overlap, chain entanglements. So the one thing that's odd is that, and I think we talked about before, is that so you'd think that once they overlap, they would entangle. Like, that's kind of like an obvious thing, right? That they're the same thing. And then we saw with polyelectrolytes, they aren't. And these are kind of polyelectrolytes. So you could answer that about in terms of polyelectrolytes. So charged chains, so there's some kind of other things going on too. I don't know, but you could just toss that around in your head. I think that whether the overlap and the entanglement are the same thing or not. And then how is it the screening length can be the same as the Kuhn length? That seems to be kind of weird. Like, that's really unusual too. So the E is just like philosophize about whatever's going on in this paper, in the end. He's got, so at the same time, so he published, this is in Press or something. And then at the same time, he's got a paper in macromolecules by the same authors, except with one extra guy from Denmark or something. And it's like the same paper, It's a little bit more in detail about the bending mode thing. But it's shorter than our paper. But it's basically kind of weird that they double publish the thing. I mean, I guess this happens. People do it for whatever reason, but there are like 2 papers that were published. This one actually has a number. So this one was earlier than the soft matter one is the same thing, kind of. So it's kind of funny that they did double publishing of it in the same year. And they were probably submitted at the same time. So anyway, all right, that's it. So thanks. Yeah, thanks for it's been a good class. Nice to have the questions and everything. I think it worked out good for me.
Thank you.
Thanks. Yeah.
For a little bit later.